Welcome to Math 106, Chapter 0.5, where we talk about exponent properties and power functions. Now, this is a crucial section because a lot of these themes do come up when we go to derive, as is with all of our other Chapter 0 foundational notes. However, you're going to notice that these skills come up time and time again. So when we talk about some of these properties, you may already know some of these. When we look at b to the n, b is our base here, and n is our exponent. Now this is just saying, okay, well, whatever b is, we are going to multiply it by itself however many n times. So if we are looking at example 1, if we have 2 to the third, and if it's in this notation, right, we're just multiplying 2 3 separate times. 2 times 2 is 4 times an additional 2, which is 8. Now see if you can figure out the difference in example 2. One has parentheses and one doesn't. That does slightly alter our answer. See if you can pause and try it out. Now, parentheses. This is really written as -1 times 4 squared, which means that no matter how many times you multiply 4, the negative is still going to remain. So we should get -16. Whereas if we do have parentheses, and any time going here on forward, anytime you have parentheses and it's squared like this, it's just going to take this -4 and it's going to multiply it however many times, but with the parentheses written out. In this case, we can clearly see that your negative signs will cancel, and we're left with a positive 16. Now, this is the 0 rule. So if we have b to the 0 or anything to the 0 power, it's not going to equal 0. Instead, it equals 1, which is super nice for us. And this is always true. Whether that is a variable to the 0 or a number to the 0, however complicated, if it's raised to the 0 power, it's equal to 1. So x to the 0, or sorry, 0, x to the 0 is equal to 1. And this whole thing on your other side, for example, 2, is also equal to 1. Now this negative, well, if you have a negative exponent, if you see the negative exponent, we don't typically want to show the negative exponent. So what we get to do is change the location of the variable containing the negative exponent. We change its location by showing that this is first in the numerator, and now it gets to drop down into the denominator and then become positive. So we switch the location of the variable or value with the negative exponent. I think I had too many T's there. So switch the location of the variable or value with the negative exponent. Only the negative exponent. Only negative exponent. Do not change the location if other values have a positive exponent. It's only the one with the negative exponent. So if we have x to the -4, notice that it's located in the numerator, which means that we get to change its position and then make it positive. See if you can try out example 2. Well, you'll notice that in example 2, right, it's in the denominator, which means we can bring it up into the numerator. Again, make it positive. Now, this one is super key. You will be seeing this quite often. And the reverse is true. If you needed to bring this up into the denominator to show, or numerator to show that it is in fact negative, we can certainly switch that up as well. Now, this next one is also very significant. We are going to see this quite often when we derive. This is a fractional exponent. The fractional exponent can be turned into a radical notation. So radical notation, meaning it contains some sort of root with your variable. Now, what's nice is that if you have anything that's located in the denominator, the value that's in the denominator is going to be the one that is located in the power of your root. So this is in your power, and then anything that remains in your numerator goes on the inside. Now you could also write it as c root b to a as well. That is perfectly fine, as long as b and a are kind of going together, and c is the root of, c is the power of the root. The denominator is the power of the root. And you'll notice that you can write it in two different ways. When you first write it, it doesn't quite matter. However, when you do go to evaluate if b were to be a number, sometimes you want to be strategic. You might want to take the root of it first and then take the exponent, or vice versa. So let's go ahead and try to write this out. All right, we said 2 being in the denominator will be the power of your root. So we now have the square root of x cubed. Or you could say we have the square root on the inside and cubed over here. Doesn't matter which notation, just pick one. Typically, I write it here until I'm ready to maybe switch it up if I know what x is. And one more time over here. We now have the root has a power of 5, so that means it's going to be located in your denominator, and 2 is in your numerator. So let's have you guys try these quick examples. So see if you can pause the video and try these out. So we have -5 cubed, which is really -1 times 5 cubed, which is equal to -1 times 5 times itself 3 times. So we're really working with -125. Now let's do it again here. Now we actually have two things going on. We have a negative and we also have a fractional rule. So first, let's take care of your negative. So notice that it's located in your numerator. So let's go ahead and put 1/8 to the 2/3 to make it positive. Now we can go ahead and tackle your fractional. So we have the cubed root of 8 squared, or you can also write it as the cubed root of 8 all squared. Now, which one would it be easier to evaluate? Do you want to square the 8 first and then take the square root or cubed root of it? Or do you want to square root or cube root 8 and then square it? Well, it actually doesn't matter on this case. Both are very easy to do as long as you know what your cubed roots are. So 8 squared is what? 64. And what's the cubed root of 64? What number times itself 3 times will get you to 64? Well, that would equal 1/4. Now, if you went the other way, what is the cubed root of 8? What number times itself 3 times gets you to 8? Well, that would be 2. And square 2, we're now with 4. So you'll notice that either answer or either way that you approach it is going to be come up with the same answer. Just sometimes with number sense, there might be an easier path than another. Let's take a look at C. We have 4/x to the -2. Now, before starting, what is the exponent on top of 4? On top of 4, if you're not seeing it, it's going to be that little ghost 1. Right? So is this 1 going to be positive or negative? Well, it's a positive 1. And now the reason why I'm making that connection is that this one being very clearly negative, we want to change its location, but we're not changing the location of 4 because it already has a positive exponent. We're changing the location of x to the -2 because this is a negative exponent. So your final answer should be 4 to the x squared. That way now it's positive, and then the 4 still has the same exponent. It would be a lot different if we had 4 to the negative first, right? But again, it's only the one that has the negative exponent gets to move the location. Now the last one. What exponent could I put on top of this x? Top of the x is our ghost one. Now, if we don't see a number out here, what can we assume? We can assume that it's a square root. So we should really have x to the 1/2. So these should be really quick and easy examples. They will get harder than this, but this is just kind of for us to start. Now, before we get into it, because we're talking about roots, I do want to recall some little quick facts. Now, this is a square root graph. This is the graph of of y is equal to the square root of x. So what do you notice about this graph? Well, this graph contains no negative numbers. No negative, I should say, x values, right? So no negatives. However, we do have positive numbers, meaning that if we were to evaluate the square root of -9, are we allowed to enter in a -9 under our particular square root? No, this will come up with a non-real solution. As we recalled from previously, though, we could create an imaginary solution by pulling out the negative and calling it I, right? However, based on its graph, if we're looking for, okay, is it going to work or is it not? It's not going to produce a real solution. Over here, though, comparing it to your previous graph, what's allowed, what's not? Well, you can clearly see that there is a positive counterpart. So positive numbers are still okay. What about negative numbers? Well, we do see the graph contain negative numbers. So that's okay. Now, this is the cubed root graph. Just a standard one, y is equal to the cubed root of x. So if we were to evaluate the cubed root of -27, is this allowed? Yes, right? Because if it's a cubed root graph and you see a cubed root here, negative responses are okay, negative evaluations, which now just leads us to figure out, okay, well, what is it simplifying? Well, what are factors of 27? Well, one is 3 and 9, and what's 9 made up of? 3 and 3. And you'll notice that we have 3 threes located in the square root of -27. One of them happens to be negative. So your output should be a -3. The negative following us out, that's okay to be negative, right? And then your negative here, negative here. And then your output will get us to a -3. And you can see that your values of your y on this particular graph will be a negative. Now let's take a look at some more just basic laws of exponents. So we have the product rule. Now the product rule says as long as your bases are the same and they both have their own exponents, what does it look like we're going to do to their exponents? Well, we get to add their exponents. So while we see a multiplication sign, well, yes, it's multiplication. It's going to switch to addition. Two of the same variable being multiplied by each other will add your exponents. Let's do it again. Quotient rule. If you can remember the product rule, right, you can remember the quotient rule. It's just the opposite. What's the opposite of multiplication? Well, it's division. We can see division right here, which is going to switch, right? Instead of addition, what does it look like we're going to do to your exponent? We're going to now subtract the exponents. So if you can remember the product rule, it's just the reverse for the quotient rule. Again, they both have to be the same exact variable in order for this to happen. Now, the last one is called your power rule. Anytime you have a variable with its own exponent being raised to another exponent, what does it look like we're going to do? Well, it looks like we're going to multiply your exponent. So when you have a variable raised to another, or sorry, an exponent raised to another, raised power, we're going to turn that into multiplication. We'll multiply the exponents. So with that in mind, can you guys try pause the video and do example 1 on your own? Try as much as you can. Well, here we have the product rule, right? We have two things of the equal variable that is separated by multiplication. So we can bring those together and say, okay, well, it's now going to add to make x to the 6th. The opposite is true. You have the same, and now you get to subtract. Now we need to be strategic, and I didn't point it out enough here, but which one was doing the subtracting? Well, B is doing the subtracting because it's on the bottom, meaning that which one will we subtract? We'll subtract 5 from 7. We'll end up with x to the negative 2, which we cannot have the negative 2, right? We need a positive exponent, meaning that we're going to drop it down below. Now, if you needed a system to check, all you need to do is write out the amount of x's. We have 1, 2, 3, 4, 5 above. 1, 2, 3, 4, 5, 6, 7. Cancel out 1 for 1. 1, 1, 2, 2, 3, 3, 4, 4, 5, 5. And you're left with the 2 x's on the bottom. These signify these 2 x's right here. Now this one you could do a couple different ways. You could immediately go ahead and multiply it in, or you can go ahead and drop. Doesn't matter, I'll show you both. If you wanted to multiply here, 3 times negative 3, you'd come up with a to the negative 9. And notice it's the power that's negative, it's not the variable that's negative, in which case we now have to drop it down. We also need to we also can see a different way if we wanted. We could say, okay, well, a to the 3, negative 3. We can also follow along and just bring this now under the bottom. And now we're going to change the sign of this 3. Notice that on the inside, this 3 does not change its value or sign. And instead, it comes up with the exact same answer. Doesn't matter which order you do it in. Now, the last one might be a little tricky. And you'll notice that one is in a fractional exponent and the other is not. When we're in doubt, working with fractions, it's going to be easier to work with fractions as is, as far as like adding and subtracting fractions go versus roots. So let's go ahead and make this into a fractional exponent on the bottom. Now that we have the same base, it's a base of 5 and a base of 5. This negative we can pull out front if it bothers anybody. It doesn't matter. And no, it's not just 1. Well, I can't say that. But this one is going to be, but it's not always going to be 1. Let's take a look at what we would do with your fractional exponents. We do have division, meaning that we will do some subtracting. We're going to be subtracting your exponents. 3 over 2 minus 1/2. And thankfully, right, we don't need to worry about common denominators because we already have a common denominator. We have negative 5. 3 minus 1, is 2 over 2, which is 1. So we have negative 5 to the first power. It won't always be like that. You can have different exponents. So just be aware, if you have one fractional and one radical, definitely make them fractional so that you can simplify. Now, for example, two, we are getting a little bit more complicated, and they do go kind of go on here. B is probably the most complicated you'll see for me. I might tack on something simple like a zero exponent on there, but that's probably as hard as you would see it on a test. So let's see what you've picked up from this and end on example two. All right, so first things first, with example two, what we want to see first is that everything on the inside, which I would say we should do first, is try to make sure that everything on the inside is simplified. So do any sort of coefficients need to be reduced? Do we need to divide anything? Do we need to clean it up? Do we have exponents that need to switch positions? Or do we have variables that can combine before we make anything bigger? Well, for us, really, the only one that needs simplifying is probably when we have y to the negative first, which we can change its location. We can bring it all the way up top. 2 remains on the bottom because 2 has what exponent? 2 has this positive little ghost one, so that one has a positive number. So we don't need to change its location. It's really just the y that needs to change. Now we can go ahead and distribute in that 3. Now keep in mind, this 3 has to go to every single value. This avoids having us write out this structure 3 separate times. But you'll notice that each number I'm writing out 3 times. This is the shortcut. Do I need to multiply 3 times 3 times 3? Okay, that makes us get 27, okay? And x squared times x squared times x squared, right? That's 2, 4, 6, that's x to the 6. Now I have y, 1, 2, 3. Now I have 2, 1, 2, 3, so that's 2 times 4 times 8, right? So your answer should look like this in the end. It's just, we don't want to do all that work. What if it was so much bigger, so much more complicated on the inside? Instead, what we can do is go ahead and pop it in, multiply. And I'm just going to show you that extra step. This is a little unnecessary, but just to kind of show how much faster it is, right? 3 cubed, 27. 2 times 3, 6. 2 to the third is 8. Right? It goes a lot faster than having to write it out and then multiply. If this is your thing, great. It takes a little while, especially if it's more complicated, okay? But you'll get there in the end. Let's try out B. So again, before you multiply and get started or start distributing, simplify first. What can we do to your terms? See if you can pause the video. Well, your x's can certainly combine here. So we get 1 over 8x cubed y. And the reason for that is if we were to do that small division, this is x squared minus 5, which is x to negative 3. So we'll drop that down into the denominator along with the 8 and the y. Then we're left with negative 4, y cubed, x all squared. So now before we multiply them together, we do need to tackle the raised exponent by multiplying it in. If you wanted, you could multiply it by itself, just write it all out. And what is going to happen to that negative? Well, that negative is going to disappear because keep in mind, this is acting as that very first one, that first example too that we had, as negative 4 times negative 4, where we said that negative will disappear. It just looks a lot larger and more complicated this time around, but we'll end up getting rid of that negative. So we should get 16 y to the 6th x squared. Or if you did it this way, again, 16 y to the 6, because that's 3 plus 3, and x to the 1 plus 1, and 2. Last thing we have to do is clean it up. You'll notice that when we try and merge these, this one is being divided, meaning that when we go to merge it, all of this will be above and all of this will be below. Now we can go ahead and simplify. 16 and 8 will simplify. X squared and x cubed will simplify, and one more, y the sixth and y will simplify. So we're left with 2 y to the fifth over x. And that should be it as far as our laws of exponents.